Okay, so I'm going to solve the same problem in a slightly different way using a different solution curve. Here's how we can do this. And this method only works for very simple situations, but it's worth learning how to do because on the EIT exam, you can solve a problem very quickly. Okay, so we have our basic excess pore pressure curves, and the way that we've been working it, let's assume double drainage, that I have a point of interest that's in the middle of the layer. In reality, what I should do to get a better answer is to break this layer up into sublayers. So I'd break it up into maybe sublayers like this, and then I would pick a point of interest in the middle of each sublayer. So I'd have a point of interest in here, and a point of interest in here, point of interest here, point of interest here, point of interest there. And that would give me a better result. I don't require that because it just leads to a lot of repetitive calculations. Now, if we did that, what we would find is that my answer would come out slightly different. It would be more accurate in a sense, but people have done this. Put it this way: they've taken the layer, they've broken it up into a lot of sublayers, and they've created a new curve. The new curve is instead, well, I can create a new curve. I'm just going to show the way that it works is it ends up that if I take a lot of sublayers with points of interest, then what we end up considering is the area. In this case, the blue area. So in other words, let's just say my capital T is 0.15. Then that means my excess pore pressure curve that I'm interested in is this one. Then if I take this blue area, compare it to the white area, and the blue area related to the white area, or the total area rather, I guess is a better way to say it, that will tell me the actual percentage of consolidation. So for instance, if this blue area represents 40% of the total area, then I have what's called 40% consolidation, meaning that I have 40% of my delta H at time infinity. So for instance, for T equals 0.15, we have 40% consolidation. For instance, suppose that T equals 10 years, T equals 0.15 as an example for a particular problem. Then that would mean that my delta H at T equals 10 years is equal to 0.4 times my delta H at T equals infinity. So we can solve problems, these simple problems, very quickly. And this is how it's done. So in other words, people have taken the areas. People have figured out all these areas for the different T's. And they come up with this solution curve. So in other words, and all I have to do then is to get my big T. Say if my big T is 0.4, then I go over here, I have 70% consolidation. So that would mean all I have to do is find my settlement at time infinity and multiply it by 70%, and that gives me the settlement at my time of interest, or capital T is equal to 0.4. All right, but we can only use this curve for a fill surcharge type situation. we cannot use this method for building settlement. So if you're just given a fill settlement problem, you can use this method. I'll show you how to do it. Okay. Back to our problem, 8 feet of clay, adding 5 feet of fill. We solved this problem before. We got a delta H ultimate at t equals infinity of 0.655 feet. Okay, so here are all our solar properties and everything like that. So okay, here's how we solve the problem. We're going to use this chart instead. And so we're going to use our basic equation, capital T is equal to C sub VT over HDR squared. We note that it's single drainage, HDR is H, which is 8 feet. There's my H, 8 feet. And again, I go through my times, 1, 5, and 20 years. I get my capital T's, just like we did before. They are the same. But now I go into my chart. So I got T is equal to 0.0469. Well, where's that? That's in here someplace. My T of 0.234, I'm in here. And then my T of 0.923, I'm here. So I read off my values of percent consolidation for each one of those T's. And I get 20%, 55%, 91%. And then all I have to do to get my answer is simply take, 20% times the 0.655 gives me the 0.131. And then 55% times the 0.655 gives me the 0.36. 91% times the 0.655 gives me the 0.596. It's that straightforward. Now, okay. I've already done this problem for you. What? Oh, okay, here I've asked you. Okay, I want you to pause this video and do this problem, and we're just changing the times, 8 and 15. So I'm going to assume that, okay, so pause the video, do this problem very quickly. I'm going to assume that you have done that now, and I'm going to give the answer. Okay, so it's pretty straightforward. All I have to do is convert my small t to my big T. And how do I do it? Using my big T is equal to C sub VT over HDR squared. So I simply put in 8, and I get capital T as 0.375. I come down here, 0.375 over, I get 0.67. I put in T equals 15. I come down here, 0.703 over, I get 0.88. Okay, that's all for that one.